Hi everyone, my name is Ashwantani. Today I will be presenting you my project for this course, that is compound scaling of neural networks using EfficientNets. So why do we need compound scaling? Um, so people usually start with a baseline model and then scale either of the dimensions, that is the number of channels, or they increase the depth of the convolution network, or they use higher resolution images for obtaining better accuracies based on the availability of the resources. But the problem with this type of scaling individual dimension is can be seen from this figure. As we can see that the accuracy is indeed increased by scaling either of the dimensions, but soon as the flops increase, we get only diminishing returns. So the solution to this problem is compound scaling, where we parallelly scale both width, uh, the resolution, and also the depth of the network systematically and parallelly. So why do we need efficient nets? Compound. It is not only important to compound scaling, but also it is important to choose a better baseline model for obtaining higher accuracies. So EfficientNet B0 is a baseline model for efficient nets, and which was obtained using neural architecture search. So using compound scaling on this EfficientNet B0, we obtain EfficientNets B1 to B7. And as we can see from this figure that EfficientNet B7 has achieved a new state-of-the-art accuracy of 84.4 percentage, beating the existing state-of-the-art pipelines. So how does this compound scaling of EfficientNet B0 work? So here in compound scaling, we scale depth, width, and resolution of the images by a factor phi. Here alpha, beta, gamma can be imagined as suppose we have twice more resources available. We distribute those resources in the proportions of alpha, beta square, and gamma square. And for this efficient for this scaling of EfficientNet B0, we use the following algorithm. Here we will start with v is equals to 1 and do a small grid search. Tangently obtained the values of alpha, beta, and gamma to be 1.2, 1.1, and 1.15 respectively. And by fixing these values of alpha, beta, and gamma, and using different values of phi, we have scaled the efficient B0 from B1 to B7. So the EfficientNet B0 has the following architecture. So it has convolution 3.3. That means it's a simple convolution layer with batch normalization and the serial activation function. So 3, 3 is the kernel size used here. So the batch normalization reduces the dependency of the gradients and adds the regularization parameter. And the serial activation function can be given by this formula. And MBCons are the inverted residual blocks. Here, MBCon N means the expansion factor. For example, if we take an input size of C channels, we get output of n times C number of channels. And MBCons also use squeeze and excitation blocks, drop sampling, depth-wise convolutions. So the squeeze and excitation block gives different weightages to different channels. Drop sampling sets the output of some of the samples to zero in a given mini batch size at various depths stochastically. This plot is gives a training loss versus the number of epochs when efficient B7 is used on a training cipher 10 dataset available in PyTorch. So as we can see, the accuracies are very low indeed. One possible reason is that we are using only very few epochs, but the constraint here is that efficient nets are very huge and have large number of parameters, so they take long time even on training GPUs.